Hello, welcome to a special edition of The Naked Scientists from the Science Festival in Cambridge. Everyone enjoying the Science Festival in Cambridge? OK, what we have for you is a fun-packed one-hour show in which we are going to introduce you to some of the wonders of the universe. We're going to answer your science questions, and we're going to blow some stuff up. To my right is an august panel from the University of Cambridge. Our first guest, Hayley Friend. We give everyone a wave, Hayley. Okay. Hayley is from the pathology department at the university, where she is working on the breast. The breast tissue, how it forms, how it works, what its function is. Of course, most people will say the evolutionary role of the breast is to convince blokes that a stone of fat is actually very attractive. And I understand, Hayley, you're actually making a model breast in the lab. Is that right?
We are, yes.
In the dish?
We are literally building a breast in the dish so that we can test drugs out. So we all know breast cancer is a big problem. We want to test drugs, and so we do this in a dish rather than using human bodies.
Hayley, thank you. Also with us today, we have David Weston, who is from the biochemistry department. Okay, David actually works on ion channels, presumably not something that someone with a predilection for pressing laundry has a lot of.
No, it's
What's
not.
An ion
it's
channel?
not that type of ion. No.
ION rather than ION.
ION. So charged atoms called ions.
What do these things do in the brain?
So in the brain, you've got these ion channels, which are important for making sure that all of the electrical connections between cells in the brain actually work. And what we do in our lab is try to work out exactly how these ion channels contribute to how cells are able to communicate with each other.
So how drugs work?
Yeah.
Why we might get addicted to certain things, like coffee, in my case?
Exactly. So these channels are very important for drugs. We like to target them, and we like to make them work better or make them work less effectively. So this is what we like to look at in our lab.
OK, so brain scientist. So any questions to do with how the brain and the nervous system works coming David's way. And our third guest this afternoon, Sam Gregson, who's from the Cavendish Laboratory. Sam, you're a particle physicist. You study really small stuff, like, for instance, the landing gear in an Airfix model, which is always about the size of a proton, from what I can gather, and you have to try and put these things together.
So I work on the Large Hadron Collider, which I'm sure you've heard a little bit about in the news. So I'm kind of like Brian Cox, but with a different terrible haircut. And I work on the tiny particles, as you say, and I'm trying to look at the difference between particles and their mirror image, which is known as an antiparticle, and trying to work out why everything we see around us, me and you, are made up of normal particles or matter, and why there's no antimatter around today in the universe. So trying to answer the where we came from kind of question.
So particle physics, or anything to do with the structure of matter around you, that's coming Sam's way. Before then, though, let me introduce our kitchen scientists, Ben Valsler and Dave Ansell. Their chosen specialist subject is blowing stuff up. Take it away, guys.
Well, we're going to start not by blowing stuff up, but actually by talking about something that's around all of us all the time. And we're going to grab one of our panel. David, could you come and join us for this, please? Now, David, how much weight do you think there is right now pressing down on your head?
Well, I can't feel anything, so nothing.
Nothing? That's a good guess. Anybody want to think about how much weight there might be pressing down on your head? It feels like nothing, doesn't it? Dave, how much weight is pressing down?
So what is around us? What is on top of Dave's head? There's air on top of Dave's head. And actually there's more air than you'd expect. There's probably, if you add up all the air, kind of piled up all the way up to the top of the atmosphere, there's probably about 100 kilograms of air on top of Dave's head. So it's a bit like me standing on Dave all the time. And probably on top of all of you as well. Does anyone notice that? The reason is that as well as 100 kilograms of air pushing down on Dave's head, there's also 100 kilograms of air pushing up on Dave's head, and they balance out and you don't feel it. So it's kind of a bit dull and doesn't do anything, unless you can unbalance those two, the air pushing on one side and the air pushing on the other side. I'm not going to stand on Dave's head because that would be a bit harsh. But we do have a high-tech piece of apparatus which will unbalance these forces.
So, David, I'm going to hand you a microphone so that you can describe to the people at home what it is that you can see. High-tech piece of apparatus.
It's a vacuum cleaner.
It's a vacuum cleaner.
It's a vacuum cleaner.
Hopefully most of you have got one of these at home, although I'd imagine quite a lot of you come up with a good excuse not to use it.
I certainly do.
There's certainly a lot of nodding faces in the crowd today. Dave, how are we going to use a vacuum cleaner to demonstrate this effect?
So a vacuum cleaner, what it does is it reduces the amount of air inside itself, which means that there's less air inside the vacuum cleaner than outside, so air on the outside pushes in, taking all the dust with it, and it cleans the room.
So when we're talking about a vacuum cleaner sucking, it's actually not sucking, it's just the air around it, the weight of that air, pushing things into the vacuum cleaner.
That's right. So we thought we could use that, but cleaning up is a bit dull. So we thought we'd attach a large pipe to the vacuum cleaner.
So what we have done is we've got some plumbing that we actually borrowed from the back of the sinks in some of the toilets in this building. So when
Now
you
I'm
wash your
worried.
hands, you might get slightly damp feet, but don't worry about it. It's all under control. So this bit of piping actually runs at right angles to the hose for the vacuum cleaner itself. So rather than going straight down in there, which would mean all we could do would be basically clean up from a lot further away, maybe good for your back, but not really good on stage. So actually this end of it is open, and that's very important for what we're going to do.
I like the way it's pointing at David. That's quite good. Yeah.
I'm slightly scared.
It's all right, it's not loaded yet. So
So at the other end there's a flap, which means that air can't get in at that side. So the only open end is at this side. And if I put a projectile, which is a bit of foam, at this end, there's going to be less air on inside the tube than outside the tube. So the air's going to push it down the tube. And by the time it gets to that T-junction, it should be going quite fast.
It's depleted uranium foam, isn't it, Dave?
So the flap here is very important because it stops the air going in from this way. Otherwise, we'd have the same amount of air pushing in from both that end and this end, and it wouldn't go very quickly. The reason why it's a flap is so it can close again afterwards, which means that we can fire more than one thing. Now, David, as much as I would love to use you as a target,
Oh, thank God I'm not
I
a
really
target.
think it should be your responsibility where we aim this. So please
Okay.
come and take this and work it out. Now, you get to aim the vacuum bazooka. Who would you like to aim at?
Oh, that's a difficult question. Who wants to be aimed at? Oh, there's a lot of hands. I think somewhere, can we get all the way to the back?
We could try. I think for the purposes of avoiding a lawsuit, then the best thing would be to aim it at someone who signed a disclaimer, such as someone with a red jumper. As a
Oh,
sort of,
yeah,
sort of thing
that
we're
seems
looking
like a
for.
good
a nice,
idea.
bright red jumper on the stage.
Do you want to swap jumpers, anybody?
Now pop it on your shoulder like a proper bazooka.
Wow.
Here we go. Now what's going to happen is Dave's going to switch the vacuum cleaner on, and as we said, the air pressure will push down behind that projectile. It'll shoot along the length, hopefully out of this flap, and wherever David aims it, and we might get to score the extra points for the red jumper. So Dave, are you ready?
I like the way the panel are all
3, 2,
ducking.
1, fire it out, and...
Okay, I give in. I
Right on the
surrender.
bum.
I surrender. Thanks, David. That's David's first and last appearance on our show. Yeah. Thanks, David, for being good sport. Thank you very much. David Weston. So does anyone have any questions about the vacuum bazooka, how you can build one, how you can get one together?
Hello, I'm Andy and I'm a bit old.
You're also out of range, so you can say anything you like, Andy.
So you said that all of the air is pressing down, would be about 100 kilos for all of it. What sort of vacuum does that vacuum cleaner produce?
Okay, so this vacuum cleaner isn't extracting all of the air. A good vacuum cleaner will extract about 1/10 of the air. So it's probably about 1 kilogram or 2 of air pushing on that projectile, so it accelerates down very, very quickly.
So could you have it flying 10 times faster and hit him 10 times harder?
Yes. As you happen to mention
not
it,
volunteering,
I have a
right?
design of that with a proper vacuum pump, which I'm building in my garage at this very moment. And possibly next weekend, you might be able to see it in the physics department when I do a lecture there.
I won't be volunteering for that experiment. What's your name and where are you from?
Herbert, I'm from London. And how do you make the vacuum?
But it's quite simple. All you need is a normal vacuum cleaner, and you just need a tube with a right angle in it. So you need to attach the vacuum cleaner into the right angle. You can either do it by buying plumbing piece of plumbing from plumbing supplies, or you can actually use bits of cardboard tube and lots of tape, and that works as well. And then you don't even need a flap. You can just put a piece of card over the end, and you just make something which fits in the tube reasonably well, not too tight, and just drop it, turn on the vacuum cleaner, put something over the end to seal the front end, and then you just drop something in and it should fly down and out the other side.
It sounds like you might be a budding engineer, which means that you will be, hopefully very soon, you'll be familiar with the wonderful things you can do with gaffer tape. And this stuff, as you'll see from our bazooka, is really important for getting all of those seals right, because if you leak air, then you lose some of that power.
And if you go to the Naked Scientist website, in the kitchen science section, there are instructions on how to build it.
That's right, nakedscientist.com/kitchen science. More from Ben and Dave, another experiment coming up very shortly. Okay, time for a little bit of pathology now, and also some physiology. Hayley Friend is from the Department of Pathology, where she is working on how breasts develop, how they work, what they do, and how they can go wrong as well. So, Hayley, tell us a bit about your work, because you're in your PhD, aren't you?
Yes.
So this is work towards your doctorate.
Yes, so I am in my PhD, and so as I said, I work on the breast, but I work on a very special group of cells in the breast called stem cells. Now, stem cells can make any of the other cells we need in the breast. And this is important to be able to produce all the milk-producing cells of not just our breasts, but any mouths, to be able to feed the young. But we also think these are the cells that might go a bit wrong in disease.
Why have I got nipples, but it's very unlikely that I'm going to do any breastfeeding?
So, you have nipples because when we're in embryo, the breast starts to develop. And the breast starts to develop in both boys and girls. And it's only when testosterone is switched on that it stops developing in boys, and that's why boys have nipples. But actually, boys do have a small amount of breast tissue from that early stage. So it is technically possible for some men to lactate. So you can breastfeed, don't lose all hope, Chris.
So if I wanted to,
Yes.
just say I did,
Yes.
how could I lactate then? How would I get breast milk coming out of my nipples then?
Well, with a lot of hard work and perseverance.
Oh, yes. But sex change, not least.
No need for sex change. We call it the letdown response, which is how all our milk-producing cells are in a bud in our breasts. And they'll produce the milk, but it's only when it's physically needed that the milk will come down and go out from the nipple. Otherwise, we'd be constantly leaking milk, and that wouldn't be too brilliant. So it's the tactile stimulation that releases the milk. So if a man was wanting to lactate, you would have to stimulate your nipples, Chris.
I did hear that actually if you use a toothbrush and you're pretty keen about it, every day for quite a long time, you can stimulate milk production.
Yes. I think you seem to have read
But
into it.
some animals... No one wants to share my toothbrush now. But some animals...
Is this on the Naked Science website, actually?
No, not in the kitchen science section. A different Naked Scientist, perhaps. But some animals do lactate, actually, the males, don't they? Some bat species do.
Some bat
do this.
species do, yes. And actually, the animal kingdom, you have some fascinating methods of lactation. For example, the duckbill platypus doesn't actually have a mammary gland. What they have is a sweaty patch of fur. And they literally sweat some milk out onto their fur, and the young will lick it off. So there's all sorts of gross things that go on to do with lactation in the mammary gland in the animal kingdom.
Now, tell us more about your development of a model breast in a dish. How are you doing that, and why is it necessary to try and grow breast tissue in a dish?
Okay. So breast tissue is incredibly difficult to grow. You can't just take breast cells and put them in a dish because they won't behave like they normally do. And this is because in the breast we have structures to support their growth, which is the fat you have. And so I have started a co-culture system where you have a scaffold of hard structure, and then you can grow fat cells in between this and then grow the breast tissue. And this effectively produces a 3D model of the breast in a dish. And so now what we can do is study the basic biology of how the stem cells grow and how they contribute to the growth, but also see what makes them go wrong in cancer. And then, of course, you can put on different drugs to see how can we stop them growing in cancer.
I was going to say, this must be a really neat way to look for ways to treat diseases, because you don't have to give them to a real person. You could give them to your model breast in a dish and see if that gets treated.
Yes, it's not perfect. It's obviously not exactly the same as a real-life model, but it's an initial screen of all sorts of different compounds you can do.
Sounds a bit icky, but do you really get a breast in a dish, or do you get a sort of bunch of cells growing in the dish that happens?
It doesn't look much like... it's kind of jelly-like, but it doesn't look much like a breast in a dish. Down a microscope, it does. But,
Has anyone got any questions for us so far? We've got certainly one just down here.
My name's Liz. If your stem cell can turn to anything, how do you make sure it turns into like breast tissue and not hair or toenail or something?
Okay, so in my system or in the body? Okay, so I'll answer both. So in the body, we have specific, we call them growth factors and transcription factors, but these are basically chemicals which send signals to the cell to say turn into a breast tissue or turn into a skin tissue, and stops it going down a different path. And so that's what I add to my model system as well. I will add the specific factors that send the message to turn into breast cell. But different cells also produce these factors, which is why I need fat cells in my model, because otherwise they won't turn into breast tissue, they'll turn into all sorts of different things. So I need the fat cells to send the messages to be a breast tissue.
Who's next?
I'm Sheila and I'm 11, and I wanted to ask, like, how big does the dish have to be, like, to grow it?
So it can be really, really tiny. So my models are probably about the size of your little fingernail. So actually they're pretty small, and in that I will have quite a few different model mammary gland systems. So it's obviously not as big as a real mammary gland, but it's big enough to be able to look at it on a microscopic scale and study it.
Any other questions? Got one just up here. What's your name?
My name is Emily Taylor. How important is the genetic background of these cells? Because obviously different people respond to different drugs in different ways. So obviously the breast, I mean, how do you choose which breast cells to use?
Okay. Yes. So there are many different subtypes of breast cancer. And the main problem with these is they all respond not completely differently, but very differently to treatment. So we have different cell lines which are derived from breast cancers, which each cell line will sort of represent one of those groups. So we do all our tests on each one of these cell lines. And as well as that, we get primary tissue straight from the breast to test as well that hasn't been in culture for too long, because then they can change after they've been in culture for a while.
So you have multiple breast in dishes?
Yeah.
Okay, one up there. What's your name?
My name's Benjamin, and
Hello.
my question is, how do the cells produce the milk?
Okay. So we have very specialised cells in our body, which will take the nutrients from our blood. They will take certain nutrients out of that. They will package them up in a different way, take sort of milk fats, lots of fat in milk, and they'll package it up as milk. And so then they'll excrete this out into a hollow. So the milk-producing cells form like a balloon, really. So they'll excrete it out into the middle of the balloon, and then they'll squeeze it, and this squeezes it out through a tube towards the nipple, and that's how you get milk.
One over this side. What's your name, sir?
Henry. And my question is, where do you get the cells from? Are they from an actual human, or have you grown the actual cells?
Okay. So when we take cells at first, yes, they're from a human, but it's possible to keep growing these cells in a dish. So a long, long time ago they were from a human, but now they've been grown in the dish for so long that we don't have to take them from a human each time. They're called cell lines. So
One last question over this side, madam.
Hello, my name's Paula. I was just wondering, is there any age at which the breast would not be able to lactate anymore?
Okay. No, there's not. You could carry on indefinitely. It'd be other reproductive factors that would stop that.
Thank you very much. Hayley French from the Department of Pathology. You're listening to a version of The Naked Scientists recorded here at the Cambridge Science Festival. Shall we be a bit more experimental again? Yeah. Let's welcome back to the stage Ben Valsler and Dave Ansell for another experiment.
So we would start off. We thought we'd start off this little experiment with a clear liquid.
Would you like a stooge, Dave?
I think I'd like
Sam's
Sam.
looking like he wants to do something.
It looks like
So we have a clear liquid. If you'd have a look at that. Maybe have a little taste and tell us what it is?
You sure?
Yeah.
Okay. I'm sure it's perfectly safe.
I've drank worse, I'm sure. I think it's water.
It is indeed water. I think you're very brave, very brave.
Well, that's certainly going to be your first round of applause for drinking a glass of water on stage.
Probably your last.
Didn't even have to say got my gear while you're doing it.
So now you're probably quite lucky that we gave you the atoms in there arranged like that. Does anyone know what atoms there are inside water? Just shout out. There's hydrogen and oxygen. Inside each water molecule, there's one oxygen atom and two hydrogen atoms. Now we're going to look at those atoms. You can split them apart by putting electric current through the water. And we've already done that. And we've got a balloon over here with a little hydrogen in it.
If I can untie it.
Now, to split them apart, you've got to put in a huge amount of energy. And hydrogen can sit there perfectly happily. It's, as I'm sure Sam will tell us, is the most common element in the universe.
It is.
About 70% of the universe, isn't it?
Yeah. An awful lot.
Now, luckily for us, we haven't had to do the splitting ourselves. We actually get our hydrogen delivered in these beautiful little cylinders, which saves us an awful lot of time and effort. But you can actually, with very little effort, split water into hydrogen and oxygen. And all you need to do is pass a bit of an electrical current through it with the right anodes and cathodes, and it splits apart, giving you the two chemicals that you need.
Now, what we're putting on here might give you a slight hint as to what's going to happen next. So, what we're now going to do, and I thought we could get Sam to do this if he's finished drinking. We're going to try and release some of that energy by basically setting fire to it. If we heat up those hydrogen and oxygen molecules, they'll get hot enough to react with one another and release all of that energy. So, Sam, would you like to do the honours?
My pleasure.
Now, hold on. So we need a good countdown. So everyone in the front row might just help to put your fingers in your ears a little bit. If you're listening at home, don't put your fingers in your ears, because then you won't know when to stop putting your... Oh no, what have we done?
Okay, go for it, Sam. So, was that quite quick? That was releasing that energy fairly quickly. But it actually wasn't that quick by the standards of some chemical reactions. The problem was we've got all the hydrogen in the balloon, and it's in order to react with the oxygen and release that energy and turn back into water, we're making water then, it takes a while for it to mix. What we've got here is some hydrogen and some oxygen, and we've mixed it up, and it's been sitting there for about half an hour, so they're really, really well mixed up. And so they should react a little bit more quickly.
So in our first balloon, because the balloon itself was just full of hydrogen, it meant that it could only react with oxygen at the very outside edge of the balloon. And then obviously as the explosion moved in, it reacted more. So by mixing it, we should find instead that the whole balloon can basically react in one go, and we should hopefully get a quicker reaction, a more energetic reaction.
Definitely put your fingers in your ears for this one, really.
This is why I prefer theoretical stuff.
Okay.
Take it away, Sam.
3, 2, 1. Okay, so that's pretty cool and quite fun, but not actually that useful. Unless you actually just want to destroy things. So we've got a slightly different approach here. I've got some more hydrogen, and we've put it in a bottle, and I'm going to let air into that bottle. So we get a mixture of hydrogen and air, and inside air we've got some oxygen. So now we've got a very well mixed selection of oxygen and hydrogen.
Now, we're going to light this again, so we're going to see the same reaction as last time. But what's important here is that we've got that in a bottle, and that this end of the bottle is open. So what you may have felt in the front there, and what you certainly heard, was the expanding gases expanding really quickly. And we're hoping that it will be able to expand out of that end of the bottle, and therefore push the bottle in the other direction. Sam? Oh.
Because Isaac Newton worked out that if you push something one way, it will always go the other way. It'll push you the other way.
So again, Sam, we would like you to do the honours. So all we need is a bit of flame at the open end of the bottle.
Quite close.
This actually is rocket science.
3,
come in from the side.
1.
And that is actually how a space rocket works. A lot of them burn hydrogen and oxygen, throw it out the bottom one way, and so the rocket goes the other way, all the way up into space.
So does anybody have any questions about hydrogen, about chemical reactions, about rockets, anything like that?
What's your name?
Shapangi. What is the ratio of hydrogen to oxygen required to make the balloon burst at its loudest?
Okay, so if you want to get it to burst at its loudest, you want everything inside that balloon to react.
Yes.
Water has got 2 atoms of hydrogen to 1 atom of oxygen. So you want twice as many hydrogen atoms as oxygen atoms, and everything will turn into water. And it just so happens that means you want twice the volume of hydrogen to oxygen.
Right, okay. Thank you.
And then you get a really big bang.
Yes, sir, just over here.
Hi, my name's Andrew Brown, and my question relates to the 2 balloons. The first one was filled completely with hydrogen, and the second one was a mixture of hydrogen and oxygen. So if the hydrogen combusted completely in the first one, then one would expect that the net amount of energy would be greater than in the second one. Yet it didn't sound like that to me. Could you explain that, please?
So basically, although the hydrogen and oxygen, there was a lot more energy in the hydrogen balloon, but it was released over maybe a 20th of a second. Whereas with the hydrogen-oxygen balloon, actually that burns supersonically. And so all of the energy reaches your ear at the same time. So it burns across at the speed of sound or faster. Then you get a huge shock wave which hits your ear. So it's much, much louder for less time.
Just up here, sir.
Hello, my name is Jude Murray. I'm 8 years old. My question is, if you add more hydrogen in oxygen, would the bottle go further?
There's actually not very much oxygen in the air. The air is only about 20% oxygen. So if you add more hydrogen, you just reduce the amount of air there is in there. And so you reduce the amount of oxygen. So some of the hydrogen won't burn. It will only burn once it's got outside the bottle. And that won't help push your bottle along, so it won't actually go as far. So there's if you don't put enough hydrogen in, it doesn't go very far. If you put too much in, it doesn't go as far either.
Okay.
And you, what's your name?
I'm Lydia and I'm 9. If you used more fire to push the bottle, would the bottle go further?
So if we could get more explosion inside the bottle. So one way of doing that would be instead of mixing it with air, you could mix it with oxygen. That would give you more energy, and it would probably push it further. If you're unlucky, though, it might actually do this supersonic burning thing, which would probably blow the bottle apart, and then just have a load of pieces and no rocket.
Which would be something of a downer. Ben and Dave, thank you very much. Well, you're hopefully still listening to an edition of The Naked Scientists, and we haven't demolished your radio sets with our explosions. We're answering your science questions, and we're also talking to 3 luminaries from Cambridge University. One of them, up next, is David Weston, who we've already heard is a neuroscientist from the Department of Biochemistry, where he is working on ion channels. These are tiny pores on the surfaces of nerve cells that enable things to go in and out of the nerve cell and change its activity. So, David, why are you actually doing this? Why will this help us to understand more about how the brain works?
So there are lots of different types of these ion channels in the brain, and why we really want to study them is because we can design drugs that target different areas of the brain and these different receptors. So they're used in a lot of different types of drugs. So some of the receptors that we work on make you feel sick. So when you stimulate these particular receptors, they can make you feel a bit nauseous. So one of the drugs that we tried to design is ones that prevent this from happening, so drugs to make you feel less sick.
I've always wondered why it is that if I go reading in the car, for example, you then start to feel sick. Why does the brain decide? The logical thing to do, if you read in the car, is to throw up. I mean, it doesn't sound terribly logical, does it? Why does that happen? Do we know?
So there are lots of good reasons to throw up, and I think that reading in the car seems to be one of the more abstract ones. But for example, if you've ingested something that's poisonous, you want to throw it up as quickly as possible. And our nervous system isn't necessarily designed for us to be reading in the car, so we stimulate various areas of the brain, a particular area called the area postrema, and when we do this it makes us feel sick. So it's got a very important evolutionary message, really.
And so if you block those nerve cells that are in that sickness centre, so to speak, they actually will stop you throwing up, will they? Or do they stop you feeling sick?
They do both, so it actually works for nausea and for vomiting. So if we can block this particular area in some way, then we can try to prevent people from being sick. But obviously it's a very complex system, so it's very difficult to stop the effect completely.
So when you go and buy packets of anti-sickness pills from Boots or wherever, other chemists are available too, then they are basically molecules in those drugs which will go to these nerve cells and stop some of these pathways that you're studying from working, so they make the sickness feeling go away.
Yeah, exactly. So you've got to design these drugs to specifically target that place. Yeah.
And so how do you design a drug to do that? Because it doesn't sound trivial to say, well, I want a molecule that will go just to that nerve circuit and turn it off.
Yes, it's definitely not trivial, and this kind of research does involve throwing thousands and thousands of chemicals at these receptors and seeing what happens. But fundamentally, what we like to do is have a look at these receptors on a very, very small scale. So we look at the kind of atoms that make up these molecules, and then these channels are called proteins, which are made up of amino acids. And they're all lined up in a sequence. And what we try to do is work out exactly how these amino acids fit together to make the protein work. And then we can design drugs that bind to these receptors and then do what we want them to do.
And you start off, in cells in a dish? And then if it works on the cells in the dish doing what you think it does, you can then try it in, say, animals, and then try it in people, other kinds of animals.
Yeah, so what we do is we test these drugs against cells in a dish, as you say, with a very sort of fancy machine that tells us if it's going to act or not. And then if these drugs are successful, we can then start testing them on sort of higher organisms to test whether they're going to do what we want. And sometimes they do.
Has anyone got any questions about how the brain works, how we make and design drugs, actually how we use these drugs in different ways, and how some drugs can have a range of different uses? There's one at the back just here, this gentleman here. Let's start with you, sir.
I'm Chris. Just wondering, you mentioned about car sickness. Does it apply to other types of motion sickness, like seasickness?
Yeah, so there's a fundamental, with these kind of motion-induced sicknesses, what's happening is that within your ears, you've got these things called semicircular canals, and these are part of the vestibular system. And what happens is, when you move around, this sloshes around some of the liquid inside, and this tells your brain that you're moving around very quickly. And you feel nauseous because it signals to that type of the brain, to that area within the brain. And it's the same for seasickness and for motion sickness. You've not got your level of gravity that you think you do, and your brain's kind of misinterpreting the information.
Nat, I was just wondering, if you could use drugs to do certain things to the nerves, could you develop drugs that could stop things such as MS?
Yeah, so this is one of the important diseases that people are looking at. So multiple sclerosis works by unwrapping the kind of fatty fibres that cover nerve cells. So this is quite a disruptive disease. And what we try to do is find out exactly how the disease works and then to design the drug that will prevent that what's happening. And what the difficult thing is actually finding out how these diseases work in the first place. So it's difficult to design a drug against something that you don't understand. So what we try to do is understand it first and then design the drug afterwards.
I'm Gaia and I'm 10. I was wondering, you know wristbands that you get to stop you feeling sick in the car, how do they work?
First of all, David, do those wristbands that you buy to put on in the car actually work?
Well, my sister swears by them, so I don't know. I don't suffer from motion sickness.
Is she bigger than you? So you're not going to argue?
No, she's fine. I don't actually know how those wristbands work, but I'd imagine that they stimulate this part of the brain that makes you feel sick and tries to stop it working. Do you have any medical insight into that question? Or?
Well, I was only thinking that it might be the placebo effect, because one thing that we know is really important when feeling sick is if you actually concentrate on the sensation of feeling sick, you can make yourself feel more sick. So if you have something which makes you think, I'm not going to feel sick, you may well then feel less sick, so you're less likely to be sick. I can only think that that's part of it. Who's next? We've got one just here. Go ahead, madam.
Hi, I'm Jenny. I was just wondering, do drugs like painkillers, do they target purely these ion pathways in your brain, or do they target the actual area of pain, like if you have a hurt foot or something?
Yeah, so these drugs, these kind of over-the-counter aspirin and things like that, work actually on multiple levels. So what they mainly try to do is reduce the amount of inflammation that's occurring, and that occurs throughout the body. So you're not necessarily targeting a specific area, it just reduces the inflammation across. And obviously you're ingesting these compounds, so they're going into your gut and then being absorbed. So the effects may target parts of the central nervous system, but they also may target all over the body, really.
Isabel, and I'm car sick and I find closing my eyes help. Why do I find it helps?
So that's a really interesting question. So you may feel less sick when you close your eyes, because when you have your eyes open, your brain is constantly trying to coordinate all of your senses together. So your vision dictates everything that you see, and it also orientates all of your other senses. And what happens when you close your eyes is you shut down your visual system, so you can't see anymore. And this makes you concentrate more on what's going on in your brain and what's going on in your vestibular system, which is this thing that makes you feel sick. So when you close your eyes, it may give your brain more computational power to think about what's actually happening, and it may make you feel less sick because you're able to concentrate on this and realise that you're actually just in the car and it's not something to be sick about.
I'm Elise, and I'm 13. I was wondering, why do some people get motion sickness and some people don't?
I think it plays into personality as well as physiology. I think that if you've been sick in the car before once, I think you're more likely to be sick in the car again. I think it definitely plays into...
Especially if it still smells, David. Yeah.
I'm just not even going to engage on that. I think some people may be more sensitive to car sickness if they don't like their heads being moved around a lot, or they're not able to tolerate it. But I think it definitely plays into what Chris was saying before about people's perception of motion sickness.
Thank you very much, David. Weston from Biochemistry Department. So this is The Naked Scientists with me, Chris Smith, talking to three luminaries from Cambridge University, who are David Weston, Hayley Friend and Sam Gregson. And we also have our kitchen science gurus, Ben Valsler and Dave Ansell. Welcome back, guys.
So we've got another set of experiments for you now, and of course we could do with a volunteer this time. Hayley, we haven't done too much with you so far. And here, take a microphone so we can hear you. Hopefully, what we're going to do now should be very familiar to you, because working in a biology lab, quite a lot of the time people need to freeze cells so that they can stop all the activity and have a look at them later.
Yes.
So we're going to be playing with some liquid nitrogen. You must
Brilliant.
use that at work.
Yeah, I use it all the time. So
how would you like to,
nitrogen.
instead of working with it and being very sensible around it, how would you like to have a bit of fun?
Yeah, sounds good.
Excellent. So we have brought some liquid nitrogen with us today. I shall grab it from back here.
Oh, it's a lot of liquid nitrogen.
It is, and we're going to look at some of the physical properties around liquid nitrogen. So, first things first, we're going to pour some out. Now, has anybody in the audience seen liquid nitrogen before? Lots of you seen it before, so you'll be very familiar with what it looks like. As I pour this out, you can all see that it actually looks a lot like boiling water. So here we go.
Wow, so that's a lot of steam coming out there.
That's actually water vapour that's condensing because the air around the nitrogen is so very cold. In fact, it's very cold nitrogen gas. There we go, lots and lots. And it looks like it's boiling water because it is boiling. It's just that instead of boiling at 100 degrees C, like water does, it's actually boiling at nearly minus 200.
That's cold.
Despite it being that cold, we can actually pick it up in a little couple of plastic glasses, one inside, one at the other. and you can have a look at it, and it does look almost exactly like water.
I'm not drinking that one.
No, that would be sensible. Here we are, Hayley. Thank you very much for.
Oh, thank you. That's
joining us.
lovely.
I've just delivered Hayley some flowers because, of course, we are romantics here at the Naked Scientist.
You never get flowers. That's lovely. Thank
Well,
you.
here's the thing, though. There is one condition of having those flowers.
Oh.
We'd like you to freeze them.
Oh. Oh, okay.
Because then they may be pretty, but they're more interesting. When they're
Okay.
frozen. So
Anything
let's-
for science, I guess.
Right, so let's take some flowers. Now, this shows you what happens when certain types of tissue, in particular plant cells, go into liquid nitrogen. Now, as we said, it's nearly minus 200 degrees. So what do you think will happen when Hayley plunges her flowers in? Shout out what you think. It'll freeze, of course it will. It's
See?
going in. So, Hayley, let's...
Ready?
3, 2, 1. Now, you might be able to hear the way that that's bubbling over and boiling. That's like putting a hot poker into normal water because it's so much hotter than the nitrogen around it. And, of course, they have now frozen. Now, if we take that back, they still look almost...
They still look pretty.
pristine, don't they? They're making some strange crackling
Have
noises.
those, that's fine.
The thing is, they're not quite as structurally sound as they once were.
Oh. You smashed them?
I did. Now, those flowers have actually just shattered, and the reason they've shattered is because all of the water within these cells has now turned to ice. It's very solid. All of the tissues are very solid, very brittle, and so that they have shattered.
So we thought we'd try and find out what would happen if we froze a person. Now, there are certain ethical
Sorry, Hayley, did we not mention
reasons
to the experiment?
why we probably shouldn't use real people.
Yeah, I didn't sign up for that.
But it's all right, because scientists, luckily, don't count. So, no, of course, we wouldn't dream of doing anything. So we have found what we think is quite a good analogue for human tissue. So we want something that's got lots of different structures in there, because we've got skin, we've got muscle, we've got fat, we've got bone. So, Dave, what have we frozen?
A chicken drumstick.
So that chicken drumstick has been in our liquid nitrogen for a while. So you've just seen what happened to flowers. What do you think will happen to something like meat, a chicken drumstick? What would happen if I put my hand in here and let it freeze? What would then happen? Shout out again. It'd smash. Dave, let's see what does happen.
Try. It's actually quite tough. I'm try. It's a tougher table.
Oh.
It does
It's smashing.
kind of smash a little bit, but it's a lot tougher than you'd expect. That's because whilst all the water in it has frozen, and it's actually quite cold, so I'm going to put that back down again. Whilst all the water in it has frozen, a lot of the proteins and the collagen, the kind of connective tissue, is still fairly strong. So it's quite brittle, and if you hit it with a hammer, it will smash. But it's kind of like rock, basically. So you can smash it, you've got to try really, really hard.
Okay, so we've seen what happens with different types of tissue, plant tissue and human tissue. And I want to show you what happens when you cool down a gas. Now, this balloon is full of air. Well, mainly air. It's actually full of my breath, which is mainly air with a little bit extra carbon dioxide. Hayley, could you come and put this balloon deep into our liquid nitrogen and describe what's actually happening as it goes in?
Right.
Hopefully the audience will see it
I'm
as
going
well.
to put it in.
So what's happening to the balloon? What can you feel in the air?
I can feel it's getting smaller. It's condensing. Oh, it's going around my fingers.
So it looks like the balloon is going flat, but what's actually happening is the air inside is cooling down. As it cools down, it has less energy, pushes less hard against the side, so the balloon seems to shrink. If we pull that back out now, it's gone tiny. And
it's growing.
It's growing. If we shake it around a bit, some of you can see in the bottom there looks to be what looks like about a teaspoon of liquid in the bottom there. Hopefully some of you will have seen that. That's actually liquid air. And you've just seen that it only takes around a teaspoon of liquid air to entirely blow up this balloon. So we want to take that to the next step, to the next level, and see what happens if instead of putting liquid air in a balloon and allowing it to expand, you put it in something in which it's not allowed to expand.
Now, this is something, if you read any textbook on how to deal with liquid nitrogen, the one thing it tells you never, ever, ever to do is to put it in a sealed container.
Yeah.
So I have, as Hayley has obviously read the textbooks, so I have a small half-litre lemonade bottle here, and I'm going to put some liquid nitrogen into it.
So here we go. We're just going to put a little bit. So you've seen a teaspoon of liquid air, enough to fill a whole balloon, and we're going to about roughly 1/3 fill a plastic pop bottle Hopefully you can hear that hissing away as it boils, taking the heat out of the air around it.
So at the moment, this is perfectly safe.
You're going to have to watch us all because we're going to retire into a safe corner down here. So those of you at the back there may need to stand up to crane to see.
Okay, so it's perfectly safe until I put the lid on, at which point it will boil and boil and boil. So are you ready, Ben?
Ready?
I can be ready, yes. So again,
Okay,
those of you near here might need your fingers in your ears. Those of you up there, you might not be able to see much, but we hope that you'll hear it.
Okay, so I'm putting the lid on now. It is now dangerous. And I'm going to retire to a safe distance, as are you. So the pressure in there is slowly building up. And lemonade bottles are amazing pieces of engineering. They can stand maybe 10 atmospheres of pressure. And when they fail, they really fail. And the poor lemonade bottle is now in many, many small pieces.
Ben Valsler and Dave Ansell and Hayley Friend, thank you very much. Thank you very much. Our third guest today is Sam Gregson, who's from the Cavendish Laboratory. He is a physicist, he's a particle physicist, which means he studies things that are really, really tiny, like the science budget in the UK. No, I'm just kidding. Give us a sort of overview of the atom, because the ancient Greeks thought you couldn't divide things down any further than atoms. That's why they called them atoms. That means you can't cut it down further. What do we understand about atoms? What is stuff made of, Sam?
Yeah, that's exactly right. So everything around us is made up of what we call matter, like this table and the audience and myself. And we now know that that matter is made up of atoms. But what we actually know now from particle physics studies like at the Large Hadron Collider is that those atoms are actually made of even smaller units. We know that the nucleus of the atom is made up of protons and neutrons, and we know that the electron goes around that nucleus. We know that the electron is a fundamental particle, for example, but we now know that the protons and neutrons in that nucleus are made of even smaller units underneath called quarks. So we actually know that there's another level, if you will, below the atom. So it's not as indivisible as the Greeks would have liked to think.
It's ironic that you need something as massive as the Large Hadron Collider to smash apart the smallest things in the universe, isn't it, really? But what does it actually do, the LHC?
So the problem is, it's quite strange on a first glance, is that we can't kind of get a screwdriver into these things. You think if you want to work out how a clock works, you put a screwdriver in and you pull it apart and you look at the little bits inside and you can work out the little Lego building blocks that make up that clock. With the protons and the atoms that we look at, they're so tiny that we can't get that screwdriver in, if you will. So what do you do with a clock that's too small to get your screwdriver in? Well, you just smash it over the head with a hammer and then all the bits come out and you can look at them. So this is kind of what we do with the protons. We smash them together, one coming one way, one coming another way, and we look at the debris that comes out from those collisions, and then we can work out what those Lego building blocks that made up those protons were and how they interact and come together to form all the structures we see around us.
One of the things you work on is antimatter. This isn't just the preserve of Star Trek, is it? I mean, this is a real entity.
It sounds very much like something off Star Trek. I was interested earlier, actually. You were saying the red shirt was going to get it with the bazooka, and that sounded quite Star Trek-y to me. So you obviously dressed poorly today. But yeah, it's very interesting that all these particles, we say we have a standard model of particle physics, and that everything in the universe is made up of a small, finite set of subatomic particles. But what we now know is that each of these particles has a mirror image or an antiparticle, which has exactly the same properties but an opposite electrical charge. And the interesting thing is that everything we see today is made up of normal matter particles, so like electrons, protons, and neutrons. And we actually don't see any of these antimatter particles around today. So the focus of my research is trying to work out exactly why that's the case in the modern universe.
But antimatter isn't just theoretical, is it? We know it exists because we use it in medical imaging, for example. We know we can make antimatter. So why do you think it doesn't exist out there where we can see it?
So the idea is that initially in the Big Bang, it must have been the case from all our models that we produced equal amounts of matter and antimatter. But obviously, as you say today, we don't see any antimatter around. So the working physics hypothesis and the thing that I work on is called CP violation, and it's this idea that particles and antiparticles behave slightly differently to one another. So antiparticles disappear or decay slightly faster than normal matter particles, and this creates a slight imbalance in the early universe between matter and antimatter. And if you've read any Dan Brown, you know what happens when matter and antimatter come together. They destroy each other and produce light. So the idea is that from this small imbalance in the early universe, we got left over with a small amount of matter that makes the stars and planets and us, and lots of light. And that's basically the state of the universe today.
Any questions on particle physics, what we're all made from, that kind of thing? Let's just start with this gentleman here.
Hi, my name's Rick. I'm 42 3/4. A question about atoms. You mentioned that we used to think that atoms are the smallest divisible thing, and now we know that atoms are made of protons and neutrons, and then they themselves are made of quarks. Will there be a smallest divisible thing, or quarks themselves be made out of smaller things?
It's a very good question. There's actually some kind of theories that aren't taken particularly seriously at the moment that suggest that there is another kind of divisibility level below the quark and kind of below the leptons, and theoretical physicists like to let their minds run wild and say what if with these possibilities. The problem is that to get to these very small scales, that means you have to have very high energies, you have to get the particles very close together, and you're looking at very small distances. So to get at any sort of fine structure underneath these quarks and leptons, these very base structures, you need even higher energy, and we already have the Large Hadron Collider, which is a 27-kilometre long ring to try and get at these quarks and leptons. So to get at a level underneath, we have to go up another order of magnitude in energy. So I don't think we could fit a machine that allowed us to study anywhere on this planet. I think it'd have to be in space or looking at particles that of high energy coming from space. And those experiments are very difficult to do.
Cool thought, though. We've got one down here. Far away.
Hello, I'm Jen. We've heard a lot about the Higgs boson recently, but we still don't really know if we did or didn't find it. Why is there still so much uncertainty around it?
So the reason is because we're physicists, and we like to be, we are never basically 100% certain. So the way that we decide when we've discovered something is we use a set of statistical tests. So you might have heard things like people saying it's been proven to 3 sigma or 5 sigma or 7 sigma. So this is a statistical test of how certain we are that we found something, and usually the benchmark that we use is 5 sigma, which suggests there's something like a 0.001% chance that we haven't found it. But we can never actually, using this method, be entirely 100% certain that we have found something. So it's just physicists kind of hedging their bets and making sure they don't say something silly in the media, I think.
But you think we probably have found the Higgs?
But we're almost certain, to the extent that in everyday life we would say we have found a Higgs boson. I'm going to get in trouble for that now.
I'm Lois, and I'm 7 years old. How many electrons are there in a child's body?
Whoa. Okay. Do you want to have a moment to think about that, Sam?
Yeah. I haven't got
yes,
enough.
Jen down in the front row says to 5 sigma, please.
Yeah. I haven't got enough fingers, unfortunately. So the number of electrons that are around any different, there's lots of different atoms in the body, there's lots of different chemicals and elements that make up the body. And each of those different types of atoms has a different number of electrons around it. So for each individual atom that makes up your body, there's several electrons that go with that. So there would be an astronomically large number of electrons.
Sam, Dave Ansell wants to come to your rescue a minute. So what do you think, Dave?
Okay, so in your body, very roughly, in every gram of your body, there are 6 with 23 zeros, or maybe 3 with 23 zeros after it, electrons. You've probably got maybe 10, 15 kilograms, so 20 kilograms. So that means you're probably going to be about 6 with 26 zeros after it, electrons. Something of that, give or take. Doing maths in your head is very dangerous on the stage.
One more question just over here.
I'm Becky and I'm 10, and my question is, if people still haven't proved that antimatter or dark matter is here, then how do you know that it does exist?
So there's a lot of reasons that we know there's a lot of matter that we can't see in the universe. We can see the stars, we can see the planets to some extent. But we can look, for example, at the rotational speed of galaxies and how galaxies rotate as you move away from the centre of galaxies. And we can tell how much mass we should be able to see from the gravitational rotation and how much we actually see. And we actually find there's a large discrepancy between the two. So we know there's a large amount of missing matter that we can't see, and hence we call it dark matter, because anything in physics that's cool and we don't understand, we just put dark at the front and then everyone gives us money to study it. So we know that this matter exists from these gravitational studies, but we can't see it. So we basically know it is there, we just don't know what it is at the moment. And there's various ideas about what it could be. One interesting model that we work on at the LHC is a model which involves something called supersymmetry, where we say that all the particles that make up the universe have a twin, and the lightest of these supersymmetric particles could be dark matter. So it's a very attractive theory that we look at the LHC, for example. But there's several theories of what it could be, but we haven't nailed down exactly what it is yet.
To 5 sigma. Sam, thank you very much. Sam Gregson. Okay, we've almost made it to the end now, and we'd like to finish by welcoming back Ben and Dave, because we've got one little last experiment for you to try, and you can do this at home too, so this is really fun. And we want our panellists, our interviewees, to have a go and become real scientists for a while, rather than people who just theorise about dark stuff. We've got a dark balloon for you, Sam, to try this on. Ben.
So this is something that you can very easily do at home, and in fact, if anybody's got some spare change in the audience, this is not me begging, you can try this experiment now. So if I just throw, not the coins, but a handful of balloons into the crowd, see how far I can get them, pinch some money from your parents or something like that, and let's give this a go. So what you need to do at home is take the balloon and slide a coin into it. So just pick a coin from your wallet.
You can tell the people that have got too much money because they're using pound coins.
Yes, I should point out notes probably won't work. Yeah. So slide it in, and it's quite tricky to get it through the neck, but once it's part of the way there, you can do the next stage, blow it up. Has everyone on our panel got...
Yep.
Oh, dearie me, that looks like we've had a failure.
OK, do a bit of balloon inflation for us, panel.
So, there we go. Once you've got the coin in there, blow your balloon up. Definitely getting some success over there. Now, depending on the value of the coin you've put in there, we should see different interesting effects. Dave, what coin do you have in yours?
So I put a 10p in mine. OK,
so what we need to do, once you've got it blown up, is we're going to spin the balloon as if the balloon was wearing a hula hoop. Yeah? We want to spin it so that the coin starts to roll around inside on its edge.
So the 10p is making this squealing noise.
Now, I've done it with a 20p. That's it. Oh.
And the 20p makes a slightly lower pitch.
20p gives a ghostly wailing noise. What have we got on our panel?
5p.
Another high-pitched squeal.
So it's working. Why does this happen, Dave? What are we seeing? What's going on?
So basically, you're rolling the coin inside the balloon, and if that vibrates the balloon then sends those vibrations out as sound. If the coin is smooth, you'll just get a smooth kind of whooshing noise as the 1p rolls around the balloon. If the smooth's got little bumps on it, like a 10p coin, it's going to wobble that balloon very, very quickly. So you get a very high-pitched kind of wail. If you've got a kind of a 20p with lots of lumps on it, you've got a lower pitch kind of wailing noise, which is a bit lower pitch. And if you do it if you get a nut from a nut and bolt and put it in there, it makes a really, really loud, kind of low, growling noise.
And what's the point of doing this, Dave, apart from making people think you need to be admitted to a lunatic asylum?
So this is showing that sound is a form of vibration, and different speeds of vibration will produce different sounds.
And where will we see the same science manifest in the real world?
So anything which makes sound, when you talk, you can feel the vibrations in your throat, and if you talk a high pitch, you'll find the vibrations a lot quicker than a low pitch. And any speaker, anything else which
musical instrument like a violin or a cello?
Yeah, violins, cellos, everything will have exactly the same principle.
Ben and Dave, thank you very much. Okay, well, that is all we have for you today. You have been a wonderful audience. Thank you for joining us here on The Naked Scientist. My name's Chris Smith. Join us for more normal programming next week. Until then, thank you, and thank you to our news panel, David Weston, Sam Gregson, Hayley Friend, Dave Ansell and Ben Vousler. Thank you.